Good morning, everyone. Welcome to today's plenary session, which will start with the presentation of one of the awards presented by the European Astronomical Society. This particular one is the Fritz Zwicky Award, presented by the EAS on behalf of the Fritz Zwicky Foundation. And for this, I would like to invite on stage Franziska and Margret Zwicky, the two daughters of the name giver of the award, which are behind the foundation, which is kindly supporting the award. Thank you. So I am honored and humbled to call on the stage the award recipient of this year's Fritz Zwicky Prize. The prize is given every 2 years, so our recipient this year is only the third one to receive it. And please welcome on stage Professor Catherine Cesarsky from France. She's awarded the Fritz Zwicky Prize for 2024 for her outstanding contributions to the understanding of the evolution of galaxies via space infrared observations and for her leadership in shaping the observational infrastructure of contemporary astronomy. So please.
So hello, everyone. Did you put it low enough that I can be seen? Yes. I always end up behind the screen when I give talks. I wonder why. Anyway, so I call my talk Celebrating European Astronomy, and you will soon understand why. So first of all, I want to say how thrilled I am to receive a prize, which is the Zwicky Prize. Because probably I'm one of the few people in the room who has actually met Fritz Zwicky. Fritz Zwicky, as you know, made an enormous amount of astronomy, was absolutely one of the very, very top astronomers of the 20th century. He discovered dark matter in clusters of galaxies in 1933. He predicted supernova in 1931 and went for discovering them, put in place the observational material, discovered 122 of them. He predicted neutron stars in 1933, gravitational lensing in 1937, etc., etc., etc. Most of these things much ahead of his time, so they were recognized years later. So now I'll talk a little bit about me. My husband and I both got a degree in the Buenos Aires University, and we were lucky enough to go and do PhDs at Harvard, and then we were postdocs at Caltech. And when we were at Caltech, between 71 and 74, Fritz Zwicky was still around, coming to every seminar, and he looked exactly like that. He always had something to say. And at the end of practically every seminar, he raised his hand and said, oh, but I predicted this 20 years ago, 30 years ago, I had done it. And very often it was true. And also those years at Caltech were very useful because I learned a lot about, I was working on theory of cosmic rays and propagation and acceleration, but I was interested in everything and I got to learn a lot, especially with the infrared group. So I got to appreciate it was completely the beginning of infrared astronomy. In 74, we didn't have any way visas to stay in the US, but our intention always had been to go back to Buenos Aires. And the political situation there was such that we realized we couldn't settle there again. And soon enough, before we knew what to do. I'm French by birth, I should say. We got offers from France for both of us. Up, I'm already. Yes, so that's how we came to France, and I got hired by the Atomic Energy Commission, which had a group in space astrophysics. And at the time, really need theorists. They knew how to do experiments, but they knew help to understand the reach of these experiments in astronomy. So I created a theoretical group and ran it for 7 or 8 years and had a very good time, but got more and more interested in space astronomy and got invited to be a member of the astronomy working group of ESA, and therefore to have a chance to see what was happening in space astronomy in Europe. So I want to say, once I went to Europe, after a while, I was disappointed. I was, first of all, from the beginning, very much a European. I really always thought that, in Europe, all the countries had to work together. But I found quite soon, especially coming from Harvard, Caltech, and Princeton, where I did my PhD, in fact, my thesis, that in Europe, Europe was behind in most subjects. I mean, it was very well situated in some subjects, particularly in radio astronomy, but in almost most subjects it was behind. And much had to do, of course, with the instruments they could use, because the potential was there. And also the way of doing things. For instance, so I decided I really wanted to help to bring Europe to the top in astronomy, or at least to the same level as the Americans. We should be able to speak to them equal to equal. And one thing I did is to become editor-in-chief of the journal Astronomy and Astrophysics. And at the time, when I went to America, the people told me, oh, you are in astronomy and astrophysics. Does it continue to be so bad? Things like that. So really, anyway. So when I was in the JWST, I was delighted to see that there was a proposal for an infrared observatory. And I thought, this is really important. This is really the first thing that has to be done. And this time, Europe has to be ahead, at least the first, and not always coming either as a small component of the American effort or later. So the Americans wanted to do the Shuttle Infrared Telescope facility with a mirror of 1 meter. It was the first priority. Well, later it became the first priority in the US decadal survey. But meanwhile, Europe indeed selected ISO with a mirror of 60 centimeters in June 1983. So the Americans, after that, of course, were a bit worried. So they immediately selected the instruments for CERTIF, even though CERTIF wasn't yet completely approved. While in ISO, the instruments were selected in 85. And at the first ESA-NASA meeting after selection, NASA proposed a collaboration. And the way they said it is essentially, give us the money and we'll make a super CERTIF with you. Let's again we are the big one and you will come and help. And Europe decided to go ahead and do ISO. And it was very interesting at the time, at every international meeting, the project scientist Martin Kessler presented ISO first, because it was accepted, and then there was CERTIF. And whichever date Martin gave for the launch of ISO, CERTIF was always going to be launched a few months before. This went on and on. But then by 1990, the shuttle possibility was abandoned. And then the PIs of the instruments did what they called their death march. They came to Europe. They were told to come and see if they could come and take over our instruments. But of course, by then we had advanced enough that we didn't want them, too late. And then, as you know, it was reselected when it was first priority in Bacal decadal survey, and it was selected as a free flyer. So ISO was a pioneer mission, and in particular, at the time, we needed infrared array detectors, and you know probably that the astronomers inherited those from military developments, and of course, those existed in America, and the astronomers had access to them, but they were not to be sold to us. So I will show in a minute anyway. But, well, just on the day that ISO was selected, Meanwhile, there was the first infrared satellite called IRIS with a mirror of 57 centimeter. And it had Americans and an important European component also with the UK and Netherlands. And IRIS made a survey of the sky and in 4 colors, and among other things discovered luminous infrared galaxies. So galaxies that were not conspicuous in the optical, but that had extremely high luminosities. They were called luminous infrared galaxies between 10 to the 11 and 10 to the 12 solar luminosities, and above that, ULIRIX. And they were among the most luminous objects in the local universe, but in fact, they didn't play very much. They only did 2% of the bolometric luminosity, and they were responsible of 6% of the infrared emission, which wasn't very much in the local universe. And when they were studied, they were often associated with galaxy collisions. So I got so excited and pushed so much for ISO to happen that I got very much involved in organizing the European community to be able to build the 4 ISO instruments with Thijs de Grauw, and ended up as PI of one of the instruments. You know, I was a theorist in cosmic rays, and there I was. And also head of my group because I had to do ISOCAM after all. So that sent me into instrumentation and administration. So this is the satellite ISO, and this is the camera ISOCAM, which is a small thing like that. It was a complex instrument. It had 2 channels, and well, you can read the rest if you want, and many filters, and a continuous variable filter. And since we needed array detectors, what was important is that I worked at the Atomic Energy Commission. We also had contacts with groups working for the military, and we had a specific development made for astronomy of array detectors, but they were only 32 by 32 pixels. Never mind, these were the first to be sent to space. So here I show you the group constructing ISOCAM in 1991, just to show that it was a women-led project, because of course I was the PI. I took as a manager Daniela Imbeau, who is just next to me. And then on the extreme, the other side, oh, it's not, it's above, okay. So there, I decided not to use this pointer, doesn't seem good. You see Daniel Oterno, because we had a big contract with Aerospatiale. And in Aerospatiale, when they saw there were 2 women, they said, oh my God, no man will want to listen to these women. So they found a woman to head that group too. And it was the first time there was a woman heading a group in Aerospatiale. So the 3 of us, and of course with many, many men helping, and very important, some important ones are here, including my husband, who played a big role as well. So, and if you think about it, for a space instrument, the people signing here are all the people that were involved. And you can see, compared to the amount of people involved in a satellite or in an experiment now, it's not so much, not so many, about 50, with every engineer and technician. So in December 1995, ISO was launched, and we went to Villafranca, and the first instrument to be used was ISOCAM. And you see on the left the way IRIS would see ISOCAM at around 5 to 15 microns. You see it was just a blur, essentially. And we saw the picture that you see below, a quarter of a galaxy called M51, and it was really a spiral galaxy. And here is the complete image of that spiral galaxy. Then we started writing papers. One of the first papers we sent, the referee answered, how can one claim to make scientific discoveries with a telescope of 60 centimeters in diameter? Which was silly because, of course, they had already been IRIS, so just a bit smaller. So many discoveries with ISO, star formation in dark clouds. It was the first time we discovered the source. This is Rho Ophiuchi. So this is, and within Rho Ophiuchi, all the sources that could counted, and star formation inside the cloud. I think an interesting result also was about the Cassiopeia A supernova, where we were the first to detect dust formation from the new material expelled by the supernova. which was in the fast-moving knots of pristine material from the dead star. So I think it was an important discovery. Then we also did mapping and physical properties of star formation regions in normal and in starbursts. For instance, here you see the antenna, and if you look at the isocam isophotes, you see that a lot of the emission in the infrared was in this area that is completely dark, of course, in the optical. And then at the time, it was very important to see when you got a source to distinguish whether it was AGN or starburst, and we showed that using the isocam CVF, you could very easily have a system to distinguish them. For quite a while, there were problems with that. But the thing that interested me most of the program I was heading was the one on galaxy counts, and in particular at 15 microns. So here we measured about 1,000 galaxies with luminosity less than 2 milligensky. You see what it looked like in the field. And on the right, you see the counts. And the curve hatched is what we would have seen if further away there would have been the same amount of infrared galaxies than locally. And you can see, no, it's 10 times more. So this already told us that the distant universe is infrared. Now, to know more, we had to have a redshift for these galaxies, and unfortunately, they weren't too many. Of course, we could use the Hubble Deep Field, which we also did with isocam, as you can see. So immediately we had a set of sources, and there were also programs to measure redshift. But of course, we didn't have so many as people have obtained before. But this allowed us to see that isocam galaxies go up to z equal 1.3 with a median value of 0.8. And once you know that and you know the distances, you can also use the SED of galaxies. You see the starburst M82. That's the type of spectrum that these starburst galaxies have, and that gets more and more pointy as you go further. And therefore, out of data of 10 microns, at 10 microns, we are essentially seeing the PAH features that are these pointy things in the middle. But you can also start calculating what these galaxies would do in the far infrared where the energy is. So using systems to do that, it was possible to calculate the integrated galaxy light not only at the 15 microns where we were working, but also to extrapolate to the far infrared. And just also more or less at the beginning of our work on isocam, there was the discovery, thanks to the NIRBE on the Kobe satellite, of an infrared background, which was expected to be the sum of galaxies away. And we discovered that, in fact, our little isocam galaxies were enough to explain a large part of the cosmic infrared background. So that it really was coming from relatively nearby galaxies, especially by today's standards, when we say z equal 1. And we found that 75% of isocam galaxies were Liergs, so that the density of Liergs was 70 times larger at z equal 1 than today. So you can see it's really an enormous change. And we also looked at what was the gene contributions, looking at correlations with X-rays, and we found that it should be less than 20%. So we were really seeing the star formation. So at the time, because U-Liergs and Liergs nearby come from galaxy collisions, we thought that all came from galaxy collisions, and in the past there were more galaxy collisions. So even with David Elbaz, we wrote this little review for Science, a fossil record of galaxy encounters. And also another point we made is that the isocam galaxies belong to redshift peaks, so they are associated to structures. They are not just scattered all over. And we were there. In the meantime, of course, something very important happened, which is the VLT. Low Vulture, as you all know, I think he was the founder of EAS, took the decision for ESO. ESO had been really struggling, hadn't even completely finished its first big telescope of 3.6 meters, but he made a bold step ahead and decided he wanted to do the equivalent of a 16-meter telescope, which, as you know, ended up being 4 8-meter telescopes. The decision was taken in December 1987, and then with the construction, the inauguration was in 99. And with this, of course, and the VLT using novel methods like active optics for the mirrors, Europe in astronomy made, I think, the most important step ahead. I think ISO was already something to show that we could stay in front of the Americans, but I hasten to say that for ISO, then there was a very strong collaboration with the Americans and the Japanese, and that allowed us then to collaborate for the projects with them, but more as equals, and sometimes, in fact, on the top. And with the VLT, of course, it was supremacy on ground, and you know that this supremacy we still have. So I took one example of, of course, there are millions of examples of VLT results, and some even led to the Nobel Prize. So I just took one having to do with galaxies, since I'm more talking of galaxies. It was possible with Symphony to measure dynamical evolution and rotation curves of distant galaxies. So I'm showing you results from this paper by Forster Schreiber. So what you see is maps, of course, showing centering on different velocities. And from that, you can reconstruct the dynamics of the galaxy and the rotation curve more or less in the central regions. And we'll have to wait for more recent or future experiments to be able to do it far away and really measure the dark matter. Another important thing that had happened, of course, with the JWST, launched in 1999, worked sometime later, and as you know, the Europeans had 15% on it. But you see, they also built an experiment, and it was not a tremendous success. And this was the last time, I would say, that the European experiment was not a tremendous success. My God. Okay, sorry. Okay, so after that, Spitzer flew from 2003 to 2009, and it had an experiment like ISOCAM, but you can see the comparison between what Spitzer saw. So you see, we saw the same sources, but of course they saw many more. And in addition, they could do a surveys where they had all the wavelengths, in particular this one good, where many Europeans participated, and ESO played an extremely important role in measuring redshifts and doing maps for all these sources. So they could make counts, and they found, of course, like ISO, but this time they would go to z equal 2. And the very important thing they found is that galaxies, both at z equal 1 and also even at z equal 2, were not scattered completely in a diagram of star formation rate with respect to stellar mass, but rather on a line. And this line has been called main sequence, because it shows some sort of equilibrium, just like in the stars. And so you have starburst above, all unpoisoned galaxies below, but the other galaxies in the main sequence. And this shows that the luminous or ultra-luminous distant galaxies are not the result of collisions or mergers, but instead they grow in a secular manner, with a rate of growth proportional to the stellar mass of the galaxy. So our idea of collisions was wrong. The collisions just did probably the ones on top. So this means they must continuously replenishing their gas, and about 80% of star formation in the universe took place in main sequence galaxies. No, Spitzer didn't have enough resolution you still had to do a lot of guessing, but with Herschel, a European satellite, then you can see that it was possible to really map in the far infrared and have maps in the far infrared where the sources could really be distinguished. And this gave, I would say, sort of the ultimate results for these counts and what happens with lurks and new lurks. And you see the counts on top, and on the bottom, you see how as redshift increases, the participation of lurks, and then finally a few lurks become more and more important, and they make the infrared background. So I pass on this one. I have so many more, I will just pass them very quickly. So the next thing I got involved in is ALMA, because in the meantime, in 1999, I had become Director General of ESO. And ESO wanted to build ALMA, if possible, at equal level of the Americans. And the problem is there wasn't enough money. But fortunately, I could negotiate the entrance of UK into ESO. And I brought enough money to be able to be at 50-50 with the Americans in ALMA. So 66 antennas, you'll know about ALMA. And of course, in Europe, in addition, we had the possibility to do very good millimeter work we have with NOEMA on Plateau de Bure. So much work was done to find the amount of gas in the galaxies. And it's very interesting to see that the cosmic, and of course, you could find either using CO or using the hot dust. You could also use radio and so on, many other methods, but essentially those two and essentially ALMA observations allowed to do figures like the one you see here, which shows the mean density of gas as a function of redshift. And this figure reminds you probably of the Madao diagram, which does the rate of star formation as a function of redshift, and indeed it is the same. And what it is showing is that the gas content determines the rate of star formation, following essentially the Schmidt-Kennicut law. So things are much simpler than you could think. Well, I'll pass on this one because. So this arrived, now we got to the time of the JWST. I just want to point out, it's very interesting that if we take the MIRI instrument, the frequency range is very similar to that of ISOCAM. So it's like ISOCAM, you know, it's like a grandson of ISOCAM. But of course, for instance, I showed you supernova Caselli, I showed you before with ISOCAM, and you can see on the right what MIRI can do to it. But you can see that the main features are there in both cases, and the dust formation under that. And of course, it makes beautiful pictures of galaxies, which can be complemented at other wavelengths with MUSE, of course. MUSE, an extremely important instrument on VLT, but you heard about it yesterday. ALMA, very important. In the radio, you can see we still need more resolution, and we'll try to do that with SKA. And with that, you can do a lot of very important work on the details of star formation in spiral galaxies. There have been more surprises in the recent, and the meeting will be talking a lot about all of that. In particular, I just put two of them. The fact that thanks to JWST, discovered 6 intrinsically red candidates of massive galaxies. I mean, Ivo, Labbé, and all, very early on, with redshift between 7.4 and 9.1. And it was not expected, of course, to have such massive galaxies so early in the life of the universe. So for the future, there's ELT. ELT, the idea of, I mean, I had approved when I was ISO-DG the idea that ISO would bring an ELT, and at a meeting in Marseille in November 2006, we even decided which model of ELT to do, which was the ISO model with 5 mirrors. So this is a 5-mirror telescope that you know is being constructed. And you can see there is a lot of overlap in the frequencies also with JWST, but of course there's more in the optical and so on, and especially much more resolution in spectroscopy with LT. So it can do lots of interesting things. For instance, in this work I just showed you, it can really complete it with finding the UV rest frame of these galaxies of Labbé et al. An example among many others. And there was radio used in all of this, but it needed to be more accurate. And as you know, what is being built is SKA, which will be the biggest radio telescope. And this is what I am involved in now. I've been chairing the board now since 2017, the board and then the council. And there will be a day talking about, so I had put some examples, but I won't show them. I think I'll stop here because I passed my time. Thank you very much.
On that side. Thank you very much, Catherine, for this very inspirational talk, and especially also for mentioning the early participation of female astronomers in leadership roles, because also for me, but also for many other astronomers, seeing and reading about your work and your achievements and your leadership has been very instrumental, and to actually enabling many young girls to become astronomers, which we are very grateful for your trailblazing. And I would like to ask whether there are questions in the audience for Katrin at that stage.
Okay.
I don't see that. Thank you very much. And you will be around, so I'm sure that people
Yes.
can come and talk to you if they would like to ask you more questions. Thank you once
Okay.
more for your.
Thank you very much.
Okay, now we're going to start our second session of plenary invited talks. We're going to have three, and the first one, the speaker is already on stage. He's Michal Drahus. Sorry for the pronunciation. And the title of his talk is Small Bodies of the Solar System and Extrasolar Visitors.
Thank you. Hello, everyone. It's great to be here. As you might have noticed, there aren't many solar system talks at EAS meetings, and that's because the planetary community here in Europe has a separate meeting called the EPSC. So the main goal of this talk is first to give you a fresh update on what's going on in our solar system, and second, equally important, to connect these two communities, which I personally consider as one. And I'm very happy to be giving this talk here in Padova. We're only 1 kilometer from this venue. Giotto made these amazing masterpieces illustrating the life of Jesus Christ. And in one of the, there you go. Interestingly, in one of these famous frescoes, he depicted the Star of Bethlehem as a comet, and possibly even Halley's comet. Now, arguably, this is the most well-known painting of a comet ever made. And for this reason, Giotto, Giotto, who didn't look like this, is a very important person in cometary science. And because of this fact, the first spacecraft ever sent to a comet was named after him. Come on, even this room is named after Giotto. So I feel fantastic to be giving a talk on comets in the Giotto Auditorium here in Padova. So I will present a mix of recent results obtained by our team at Krakow, and also some exciting results obtained by other teams. So let me begin my story. Let me begin my story by presenting these two important minor bodies, Oumuamua and Borisov. These objects are fundamentally important to science. And that's because unlike the billions of comets and asteroids which formed in our solar system, these two objects formed around other stars. They were expelled into interstellar space. And as they traveled through the galaxy, they crossed our solar system. So this allowed us to study them up close with the standard tools and techniques of solar system astronomy. And so Oumuamua, which again didn't look like this, was discovered back in 2017. And the deepest image of this object ever taken, which was obtained by our team with Gemini North, also presented here, shows basically a point of light slightly blurred by the Earth's atmosphere. That's very interesting because there is no sign of tail or a coma, the characteristic features of a comet. So that means that Oumuamua was not a comet. If it were, these characteristics of a comet would have been clearly visible in this very deep image. It's, by the way, 1 by 1 arc minute, and the total integration time was over 3 hours. So it's a very, very deep image. Now, this image was, sorry about that. Ooh. Okay, good. This image consisted of over 400 individual images. So we also scrutinized brightness in every single image, and we found a very large range of brightness variation, reaching a factor of 11 or equivalent to 2.6 magnitudes. And in the population of solar system asteroids, this huge range of variation was never observed. I mean, we have good light curves for over 20,000 solar system asteroids, and none of them is so extreme. And the light curves presented in this figure were made of photometric points which have already been phased according to the best rotation period to give this double-peaked light curve. I mean, double-peaked light curves are normally produced by rotating irregular objects. Now, as you can notice, in some regions of this light curve, it doesn't repeat exactly from one night to another. So we scratched our heads for a long time and tried to figure out what was wrong with the data, but it turned out that the data are perfectly fine. And this is the real feature of Oumuamua. And it means that it didn't rotate in a simple manner, but rather it had this chaotic component to its rotation, which is called tumbling. And tumbling occurs also in our solar system, although it's very rare, but it occurs as a consequence of catastrophic collisions or subcatastrophic collisions. So it's very interesting that Oumuamua came all this very long way to our solar system and brought us this interesting message encoded in its rotation that it experienced a collision in its very distant home planetary system. Now, the spectrum of Oumuamua is extremely boring. I mean, there is no emissions, no absorption, nothing, just a slightly positive slope, which is consistent with a slightly reddish color. Now, some colleagues, based on a worse spectrum, I mean, of a worse quality, claimed that Oumuamua had an organic surface. I mean, come on, it's just a reddish color. Okay, but perhaps the most exciting feature of Oumuamua was the fact that it experienced some strong non-gravitational acceleration. And let me explain what you're looking at in this figure. So the left panels show astrometric residuals presented in the units of standard deviation, both in right ascension and declination, computed with respect to the standard gravitational best orbit. And as you can see, some positions of Oumuamua are way off, up to 10 sigma. So this is very significant. And now the authors of this study also included a very simple non-gravitational component to the orbit, which has just a single parameter. This is a power law function which scales with respect to the heliocentric distance with just one free parameter, which is the exponent in this power law. And then the orbital fit is perfect. Now, the amount of this non-gravitational acceleration is huge. Some comets experience similar non-gravitational acceleration, but in that case, the reason is very clear because comets lose a lot of mass. So small comets approaching sun to small distances, they can experience similarly high non-gravitational acceleration. But Oumuamua showed not even a slightest sign of mass loss. So what caused this non-gravitational acceleration? Well, Avi Loeb believes that Oumuamua was simply a UFO, which it actually might have been. Nobody knows for sure. But what we are certain about is that there is no known analog of Oumuamua in our solar system. Or perhaps there is one. So back in 2020, a small asteroid was discovered, which also showed a very large range of brightness variation, 2.5 magnitude, so almost as high as Oumuamua. And it also experienced strong non-gravitational acceleration, although 100 times weaker than Oumuamua, but importantly, in the absence of any signs of mass loss. So some people were happy that we found kind of an analog of Oumuamua in our own cosmic backyard. But the scary thing is that soon this asteroid was identified to be the upper stage of the Centaur rocket, which was launched in 1966. So the best analog of Oumuamua in our solar system was actually made by our civilization, a civilization which also succeeded in ejecting some spacecraft on their way to interstellar space, I mean the Voyagers, or more recently, New Horizons. So it's very interesting. Now, Borisov was discovered 2 years after Oumuamua, and in this first initial investigation made by our team, again using Gemini North, it appeared remarkably familiar. So in this histogram here, you can see the color of the dust around comet Borisov, indicated here by the arrow, plotted against the distribution of colors measured in solar system comets. So as you can see, the color is absolutely typical. Also, the shape of the dust environment is very typical, and other properties as well. So putting its hyperbolic orbit aside, Borisov appeared completely indistinguishable from native solar system comets. And this is also very exciting, especially after Oumuamua. Now, as Borisov approached the sun, first emission features also became visible, and the first one detected was the emission of CN, which is, again, a very common radical in solar system comets, and the emission band in the near ultraviolet is also the first one normally detected as a solar system comet approaches the sun. Subsequently, also other molecular emissions were detected in the spectrum of comet Borisov, all listed here, and they all are absolutely typical for solar system comets. Now, at some point, our team thought that we found something which completely distinguishes Borisov from solar system comets. So in this very deep spectrum obtained with X-shooter at the VLT, we noticed some very compact, I mean spatially compact, faint emission features which had never been reported for any solar system comet before. And for a long time, we were debating what causes these emission features, but we couldn't find any known molecule. And finally, a student in our group, Piotr Guzik, checked the spectrum of comet Gullieuszik and told me that he found the same emission lines in the spectrum of that comet. Now, the difficult part was that the spectrum of comet Gullieuszik was a big table of data. So it was like, the beautiful mind moment when he noticed the same frequencies in this huge table. But what was surprising was that he said these were emission features made by gaseous atomic nickel, which didn't make any sense because, comet Gullieuszik was a sun grazer. This comet approached the sun to an extremely small distance where the temperature was so high that the rocks and dust started evaporating. And we know from meteorites that this rocky material contains nickel and also iron and other heavy elements. But Borisov was beyond the orbit of Mars. So obviously the same mechanism couldn't operate to explain these emission features. Anyway, we made a fluorescence model which showed a perfect fit to the observed spectrum and which also allowed us to identify additional fainter emission lines. And so we published that paper, but thinking at the time of submission that this is something, totally out of this world. But within a week of our submission, a paper by another team surfaced out and showed that these emission features are also common in solar system comets. And they analyzed 20 years of data also obtained at the VLT. I mean, what took them so long? That's another story. But it's interesting that in the end, Borisov turned out to be even more similar to standard solar system comets than previously thought. Okay, Borisov also experienced an outburst and a small piece of its nucleus separated, which might seem like something strange, but this is in fact a very common behavior of solar system comets. Good. Okay, so now let's focus on comets and asteroids native to our solar system, because there is also some interesting progress in this area. So, for a long time, it's been generally accepted that comets and asteroids are totally separate bodies. Comets containing ice, which, when close to the sun, creates tails and all this gaseous environment and also lifts dust from the nucleus surface. And asteroids being basically, rocks flying above our heads. To me, asteroids were always kind of boring because, there was nothing interesting going on with these bodies, while comets had this dynamic component to their nature. However, recent discovery, and by the way, also the orbits of comets and asteroids are dynamically separate. I mean, there is no way to make a cometary orbit, which is shown here by these blue lines. There's no way to perturb it in such a way that it becomes similar to an asteroidal orbit, which is shown here for many asteroids by these yellow, yellow circles. So there is no dynamical pathway to make one from another, or vice versa. But recently, some asteroids were observed to have tails, which is very surprising. The group of so-called active asteroids is small. It's just maybe 20 or 30 objects known to date, but some are very interesting, like this one, for example, which, besides the fact that it has this long tail, or rather trail, it's a tiny little difference between the two, it also shows some fragments. So these fragments are in fact baby asteroids still cocooned in this bare dust trail, and they were ejected from the primary object because of the primary's fast rotation. So we actually can witness the formation of a new asteroid family in these Hubble Space Telescope images. And it's probably the first certain case of an asteroid family which is created by fast rotation and not by a collision. But there are also other asteroids with tails, like this one, which have this comet-like features for a relatively short period of time around the perihelion. And then as they move slightly away from the sun, these features disappear, and then they reappear again in the same part of the orbit. So there must be another reason for this activity because it's recurrent, unless these are the most unfortunate asteroids in the whole universe. I mean, if you get impacted or something bad happens to you every few years, then it's really bad luck. But no, we think there is a different mechanism, and this is, I mean, the standard explanation is that this is the very same mechanism which generates the activity of standard comets, which is sublimation of water ice. And that's an interesting hypothesis, because if true, that would mean that the main belt of asteroids is another source of comets in our own solar system, and also another source of water. What's even more interesting is that this is this new source of water is closest to our planet. Now, this hypothesis has been recently confirmed by Webb by the detection of water vapor in one of these objects, and it's shown here by the white line. The same water emission feature is observed in the spectrum of a standard comet, shown by blue, although the comet also has a strong emission feature from CO2, which is absent in the spectrum of the asteroid. Anyway, it seems that we have another reservoir of water ice and nearest to our planet, which I think is quite exciting, especially if we recall that there is another important line of research in minor body astronomy and planetary science in general, which is the origin of water on Earth. So unfortunately, there was little progress in this line of research over the last decades, despite very intensive efforts. Now, it's been generally accepted that our planet accreted basically dry, and yet there is plenty of water around, right? Even here. So, but we don't know where this water came from. And comets are natural suspects because they are made of water ice. But in order to verify this hypothesis, we need to check if the isotopic composition of cometary water matches that of the Earth's oceans. Fortunately, the deuterium to hydrogen ratio in cometary water has not changed since the time the comets formed, and because they are basically, frozen time capsules from the epoch of solar system formation. And the same is true for the D2H ratio in the terrestrial water. So it's a very simple, a test to check if these two waters match. But it's very difficult to measure the D2H ratio in comets because there is not many deuterated water molecules in these bodies. So, no, again, okay. So, so far, these measurements were obtained only for 12 comets, and all that in great effort, with great effort. And initially, it seemed that the D2H ratio is a factor of 2 higher in comets compared to the Earth oceans, the value of which is indicated by this horizontal line. However, these initial comets were all from the Oort cloud, which is one cometary reservoir, but there is also another cometary reservoir in our solar system, which is the Kuiper belt. And the Kuiper belt is the source of Jupiter family comets. So the first measurement of the D2H ratio in a Jupiter family comet was highly anticipated. And when it finally was obtained with Herschel, it was a close match with the terrestrial value. So my colleagues thought, yes, we found the source of the Earth's oceans, and these are Jupiter family comets. Now, unfortunately, things didn't go so well from then on, because the next measurements show highly discrepant values, and for one of the comets, the D2H ratio was measured for the first time using 2 different techniques, and the results were inconsistent. But then my colleagues said, okay, never mind, but these comets here are again from Oort cloud, so we already forgot about them as a potential source of our water. But when Rosetta obtained the second measurement in a Jupiter family comet, it was even more of the terrestrial value than the earlier measurements in Oort cloud comets. So at that point, nobody knew what was really going on in this line of research. However, the final measurement obtained with Sophia by Darreglis et al. In a third Jupiter family comet was again spot on with the terrestrial value. Interestingly, these two comets with Earth-like water, they have something in common. They are both hyperactive. I mean, there is more material sublimating from a square meter of their surface compared to ordinary comets like comet 67P. So there might be something in this business of D2H ratio that we are starting to see, but the sample is of course too small. So in the last minutes of this talk, I want to tell you about the future Space Telescope, which has been recently funded under an ERC consolidator grant. And this small telescope will be very powerful because it will be specifically designed to detect hydrogen and deuterium around comets and asteroids. And thanks to these unique features, it will be able to advance all the lines of research which I have discussed throughout this talk. So Hyades will be launched on a low Earth's orbit, but thanks to a very clever design and large field of view, it will be able to trace water through the Lyman alpha emission of hydrogen and deuterium. And well, the choice of hydrogen and deuterium is obvious because these atoms are released in the comet atmosphere when water molecules sublimate and dissociate. So these are very good tracers of water. Now, this is my final slide. So Hyades will be able to detect water ice sublimation at the level of 50 grams per second and HDO sublimation at the level of 30 grams per second. These values here are given for a model comet 1AU from the Sun and the Earth. Now, it will be so sensitive, first, because of the extreme brightness of the Lyman alpha line. Second, because of the very long ionization lifetime of hydrogen and deuterium atoms, which is about 2 months at 1AU from the Sun. Also, Hyades will have very large field of view because all these atoms are distributed over a large sky area. For instance, when comet Hale-Bopp was observed in Lyman alpha, it was the size of this cloud was more or less the same as the size of a small constellation. So these are, these objects have very huge angular dimensions. And finally, thanks to the action of a specifically designed absorption filter, we will be able to eliminate geocoronal emission and observe on a very low sky background. So Hyades will be about 100 times more sensitive to hydrogen and deuterium compared to Hubble, for example. All right, thank you.
Thank you very much. I think we have time for a couple of questions, 2 or 3. Oh.
Hello, thank you for that really wonderful talk. So we found 2 interstellar objects, kind of.
Where are you?
Where I'm here.
Oh, okay.
Hi, sorry.
Hi.
So we found 2 interstellar objects kind of reasonably quickly, within a few years of each other. So when do we expect the third?
Okay,
do we expect a third?
So LSST is expected to discover between 0 and 70 interstellar objects per year. We have a two to object statistics, so we don't really know, but it's certain that LSST will increase the number of known minor bodies by a factor of 10 in every minor body population. So if that works for interstellar objects, there should be, a very big stream of discoveries coming up soon.
Yeah, last one.
Hi. Regarding the origin of water on Earth,
Oh,
there are some laboratory measurements that indicate that the Earth may not have accreted so dry, but it contained hydrogen, which may have outgassed and reacted into water. So, so not all of the water may have been delivered by comets. Could you comment on that?
right. So there are geological explanations as well, but it's believed that this primordial water accreted at the time of Earth's formation would be inside the crust, not on the surface, because the surface was extremely hot at the early years of our planet. So all the surface water must come from outside. That's the general consensus in this area. It's interesting that the D/H ratio in water was a strong function of the heliocentric distance in the early solar system. So we might be able to distinguish the surface water from the crust water. And there are results from Karen Meach who actually succeeded in measuring the D/H ratio in the water from crust, and it was different from the ocean value.
Let's thank our speaker again.
Thank you.
Very much. Now let's move on with the second speaker of this session. It's Paola Caselli from the Max Planck Institute for Extraterrestrial Physics in Garching, Germany. The title of the talk is Interstellar Medium and Astrochemistry from James Webb Space Telescope.
Thank you very much. So for me, it's a great honor to be here to give a plenary lecture in this amazing event. And I'm also honored to give some of the results for the JWST. I would like to thank many people who helped me actually to put together some beautiful slides and movies. And I'm also super happy to see the astrochemistry community growing so much. Seeing all these young astrochemists around, it's really, I don't know, I just can't sleep. I'm so excited. So hopefully these will work. Yes. And I would like to start with a small slide just about the definition for those of you who are not in the astrochemistry field. So astrochemistry is the study of molecules in space. There are two major things that we like to do with the astrochemistry. One is to use the molecules, these amazing tools that we know, where we know the frequency with high precision, and we can use them actually to probe the clouds, regions where stars are forming, in interstellar medium, planets where planets are forming. And the other is that we can actually witness the dawn and the birth of prebiotic chemistry. So I don't think there is something more exciting than this. Okay, so the other important point about astrochemistry is that it's interdisciplinary. So we need to work together, and this is the other fun part of astrochemistry. We need to work together with astrophysicists, physicists, chemists, and experimentalists. That in fact we have to use the best telescopes in the world, including JWST, but also ALMA and also IRAM NOEMA. And also we have to reproduce conditions in space in our laboratories. And then we use the laboratory to study, measure new frequencies of molecules, and also reconstruct ICEs, interstellar ice analogs. And theory is super important because we have to build up, say, models of the objects that we are observing. We can have the best astrochemical network available, but if we don't know the physical conditions in our source, we can't do the modeling and we can't do the radiative transfer. precisely enough to actually constrain what we are looking at. And of course, we need the quantum chemistry to actually help us to to calculate collisional rate coefficients and the processes that are happening in the gas phase and on the surface. So here we are. There are more than 300 molecules detected in space. If you want to know them all, you should connect to this site. That is the Cologne database for molecular spectroscopy. There are also 73 molecules detected in external galaxies. So you can see how many you can use to actually look. And if you know a little bit of astrochemistry, you can just pick the one you need for your specific object. It's just impressive. One thing, of course, we are not going to read all these molecules there, but the one thing that is very important is that the majority of them contain carbon. So they are organic in nature, and some of them are precursors of, indeed, the prebiotic molecules. There are amazing new results coming from radio, which is, for example, this benzonitrile from Brett McGuire with the Green Bank telescope, or amazing work done with the JWST 40-meter telescope in Spain from Pepe Chernicharo and collaborators. This is Indian. And then we have also ALMA with the Victor Villa and from CAB in Madrid, who discovered, for example, ethanolamine, which is one molecule that is actually in all of us, is in the membrane cell. And this is in space in a star-forming region. So our dream, and this is the dream of many of us in this room, is that we really want to understand how things came to be like this, starting from a cloud where you have this diffuse material, gas and dust, little dust grains sub-micrometer size, molecules forming, and then eventually in one side of this cloud you have the contraction of material, you have a dense core, dense cloud cores, and then this becomes prestellar because it starts to contract gravitationally. You form a protostar, and then, but you still have material coming down from the cloud, as Jaime Pineda has shown, and then you form these beautiful disks that have already substructures already at the very early stages of their evolution, like the work shown by Dominic Segura-Cox, and then we go to our later stages, so planet-forming disks, and finally planet-forming disks, so where actually we see, this is a beautiful image from Miriam Benisty, showing a planet-forming disk with two planets that are forming right now. Lots of talks. This is why I'm so excited. Lots of talks, lots of big posters in these sessions, and I just put here, I couldn't put more, I filled them all the space available here, but please go and see as many as you can, because there is a lot of excitement also from the point of view of the JWST result. And as you can see here, this link that goes from, say, the cloud to the planets brings together also this evolution in the chemical complexity that is ending here with the nice DNA molecule, but the pieces of the DNA molecules are actually seen in the primitive material of our solar system. Right, so let me start from scratch. And this is the dark cloud. So in a dark cloud, things are cold. We measure temperature down to 6 Kelvin. And you don't see much in the optical. You really need to go to longer wavelength here. But one thing that happens is that dust grains, that, as I said, are some micrometer-sized particles, they become, in this region, little snowballs. These little snowballs are then dust grains, silicated or carbonaceous material, covered with thick icy mantles. They contain lots of volatiles. How much of these volatiles they contain? Well, a lot. We measure that in the center of this core, we have almost all volatiles, so all species heavier than helium, that are actually depleted on the grain. So this is just measuring one molecule, and then with modeling, we can actually reproduce this only with this high depletion. So dust grains are covered with thick icy mantles in dark clouds, storing molecules for the next stages of planet formation. And this is when the JWST comes to hand. because we cannot really see much deep inside these dark clouds. Their extinctions overcome 100 magnitude if you go in the center, so there is no way you can see through. And so my first example of beautiful work done and being done is the Ice Age collaboration with PI Melissa McClure. And here you have in the background the chameleon molecular cloud. And here is in full glory the spectrum that was published in 2023 by McClure et al. In Nature Astronomy, where you can actually see the full spectrum along the line of sight of two objects, extinction of 60 and 95 magnitude. So these are background objects. And you see amazing signal-to-noise lines, signal-to-noise ratio line, with, of course, lots of water stretch. You see here. This no, doesn't work, so I better I don't touch much. So, but you can see here the water stretch, the 12 CO2, and also we have the bending of the water, methanol, methane, etc. But the surprise, so these features were, in a sense, with much less signal to noise, were seen previously. But the surprise was these other extra wiggles, a little bit fainter lines that we could see in the JWST spectra, and they are coincident with the features that are seen in laboratory spectra. So this is the famous database in Leiden. And you can see here, for example, so we have acetaldehyde, ethyl alcohol, and acetone with features one on top of the other. And in the bottom here, you have the observed spectra. So we can actually match these features, showing for the first time, and there are more and more papers actually confirming this, that the complex organic molecules, so these molecules with more than 6 atoms in size, are actually present inside these ices. You can do even precision measurements for the grain size distribution. This is the work by Emmanuel Dartois and Jenny Nobel, where actually you can see distortion in the spectrum. And this is a spectrum of CO2 at 4.27 micrometer. And you see that, okay, if you are in a diffuse cloud, so the flat curve here, you see nothing. Because there is no ice. But then when you go enter in the molecular cloud, you start to see the feature, flat, and then absorption. But then if you go deeper and deeper, you start to see this deviation from, so this is due to the scattering because of the presence of large grains. So there was, in this paper, there is a demonstration that if you actually measure the maximum size in the grain size distribution, the A max was found to be 1 micrometer. So this is precision measurement in the sense that you can map where you can start to see this increase in size within the cloud, which is of course important because it tells you about the dust coagulation process before the formation of a protoplanetary disk. And, okay. Now, this doesn't like me anymore. So I don't know, it is stuck, I'm afraid. So I don't know what to do. Yeah, okay, fine. So maybe there was some suspense because in fact now I wanted to show something that is, you shouldn't take pictures. Please don't take pictures because this is going to be published in 2 days. So don't take pictures. And this is the detection of the elusive dangling bonds of water in ice. We have seen these dangling bonds since a long time in the lab, but never in space, because they are very hard to see compared to the stretching of the water. You basically see very little here in the figure up here. You can see very little, spectrum, very faint spectrum, but now with JWST we see it very well, and we see actually 2 features. One is due to the presence of the water on surfaces or say pores within the ice, and also water attached to other species besides water. So this is actually very important because it tells us about the structure of the ice, and of course This is what we need to model better the chemistry in this region. This very fast, just to show that another paper that has been submitted, so again, no pictures, I don't show any data, just show you what these people are going to do. They are going to map water, CO and CO2 ice with JWST in the chameleon cloud. These contours here are extinction contour, and here we have the footprint where the water, CO and CO2 will actually be mapped. And this is again, will be super useful to understand how ice will form and evolve as you go deeper and deeper into the cloud. Moving toward the protostars, so now we form a protostar in the center, and now we can use the protostar actually as our source, it's a light source to see absorption. And here what we have two protostars that have been studied in this beautiful paper by Bill Rocha and collaborators. Please see his talk in the S6F session. And here you can see that in the top of spectrum here we have a high mass protostar, in the bottom we have a low mass protostar, so like solar type protostar. And you see a spectrum where, for example, already you can see differences. The red one is the most evident, so more methane found in high mass protostar, and more complex organic molecules in ice in the low mass protostar. And here in the left, you can see actually a diagram showing the fractional abundance of complex organic molecules with respect to methanol in the low mass protostar versus the ones that have been measured in the COMET, the 67P. And you see pretty good agreement between the two. Correlation that was also found in the past, especially with the D/H ratio that was mentioned before, and by Mariya Doroslovskaya and collaborators. So it seems, what is this telling us? This is telling us that this ice that is formed in the pre-stellar phase, then delivered into the protostellar phase, is actually kept, at least partially, in later stages of stellar evolution, where you have actually a stellar system formed. And beautiful work in high mass star formation, also done by Carolina Gieser, who is here, and you should see her talk in S11E, where you can actually use JWST to disentangle. When you look at the cluster forming region, when you have massive star formings, they are far away, you see very little. If you use NOEMA, this is great, IRAM NOEMA, because it tells you where the cold gas is. You need JWST to see where the hot gas is, where the warm gas is, then map it and reconstruct this 3D structure to actually understand what is going on, what we are looking, and how the hot gas is influencing the cold gas and vice versa. So this is impressive work, and this is the spectrum that you have from JWST. If you have like 2 point something arc second beam size, just blur a little bit and you see everything. You see the hot material with the H2 lines, you see ionized gas, but you see also ice. Okay, so JWST is for ice, excited, warm chemistry, shock chemistry, and then we need ALMA, we need NOEMA to actually map the cold gas, millimeter and sub-millimeter. PDRs for all. So once you have these big, massive stars formed, they influence the structure of the surrounding cloud. We have, in this case, amazing work that have been done in this JWST ERS program. And here, thanks to Javier Goyochea, who has given me these slides just to show some of the results. First of all, the amazing angular resolution of JWST that show how the Orion bar, which is this molecular cloud bathed by the strong radiation field from the massive cloud, massive trapezium cluster, is actually affecting the structure, the chemistry, and the physics. So we can learn a lot actually now with this detailed observation. So also there have been new detection of protoplanetary disks, amazing images of objects like this one, where you can see actually the photoevaporation of the disk. And think that 4.6 billion years ago, we were probably like that, because our sun was born in a big, massive cluster, so we were blasted by radiation from massive stars. So it could be that, this will be the future sun, and this is very exciting. One thing I wanted to point out, many papers published, but also many talks during this EAS meeting. And I would like to point out also Asunción Fuente, this talk in S11F, where she will actually talk about the sulfur seen in this region. And the other super important detection that come from this program is the first detection of interstellar CH3+. Now, if you're not an astrochemist, they say, okay, fine, it's another molecule. No, it's not another molecule. It's a molecule that you need to actually start the organic chemistry. And we have it in all chemical model. We have CH3+. Since 40 years that we are looking for this molecule, never found. And now with JWST, yes, it's here. It's in a disk. It's in one of these protoplanetary disks that has been found. And you see, this is the observed spectrum. This is the model spectrum. And this work is basically showing how astrochemistry work. You need the experiments, so you need to go to the lab, look at the lines from the lab, but then you need amazing telescopes like JWST, and also you need the theory, because there have been modeling going on to help also in the, interpretation of the data. So this is the spectrum. You see also a lot of PAHs in this disk, CH+, COOH, that comes from the photodissociation of water. Okay, so now we go a little bit beyond the, protostellar phase. We are now entering the pre-main sequence. So we are getting in stage, so we do this journey. And now the next is MINDS. This is the MIRI, Mid-Infrared Disk Survey, led by Thomas Henning. And here I would like to thank Inga Kamp and also Sierra Grant, who have been giving me beautiful slides. So this is looking at about 57 disks, and from Herbie Gaibi's disks, and also Titori disks, and very low star disks, and also some debris disks. So it is difficult to pick and choose which one to look at. So because it's impressive. Each one of these spectra from each of the disks are actually totally different. So we are now at this stage that there is really a lot of work from the theory side. This is the time when observations are actually moving so much faster than theory, and we really need to understand what's going on. So for example, in Titori stars, every Titori star disk has water. There is lots of water, but there is a variation in the amount of hydrocarbons that are present there. In the very low mass star disk, there is basically no water. There is a little, maybe tentative detection, but there is a lot of complex organic, actually hydrocarbon chemistry, as I will show you in the next one. And this is the understanding, at least identification of this line is thanks to this amazing work done in the, theory chemistry size from, for example, the Prodimo code, etc. And so the next slide shows something that I'm sure Aditya Harabavi will show in his talk, and also thanks to Jayati Akanvar, who will also give a talk in S11A. And this is shows the spectrum in one of these very low mass stars disk, just to show you how rich it is in hydrocarbons. So you start, and you also see the motion that are producing these vibrations that come into the JWST mirror, and then we see it. So you see here the first the methane, then other hydrocarbons, ethane, and we start to see here impressively the benzene molecule, CO2, of course, and many other structure. So this is the full spectrum that is obtained. You can see the high signal to noise. And I would like here to conclude in this list of say beautiful images is the one that has been done by Giulia Perotti. Here, first we have the ALMA from Benisti, Miriam Benisti paper, and then this amazing spectrum of water, lots of water lines that Julia is so talk in S11A has shown. And here we have the disk where actually two planets are forming right now, suggesting that we have a large water reservoir present for these planets. So just to conclude, what can I say? I mean, JWST is impressive. It's complementing amazing astrochemical progress already carried out with the radio and millimeter telescope. And in particular, it gives us the possibility to actually understand, this will be done, the interstellar ice composition. This is being done, but we really need to understand the processes, warm chemistry, molecular clouds, star-forming regions, and inner planet-forming disks where terrestrial planets are forming, because then we want to link to the planet formation. So for the future, well, much experimental, as I wrote here, and theoretical work is in front of us, because we need really to understand what all these fingerprints from different disks and cloud and ices in pre-stellar material are telling us. We have to put these things together. And we also wanted to understand from here the role that these ices have in the evolution of solids during the process of planet formation. This is important because we want to know the composition of terrestrial planets. We want to know the composition of their atmospheres, and we want to know how life originates, and if it can originate not just here, but probably in other places. And I don't want to stop my talk without remembering somebody who have given basically us the base to move forward. This is Harold Linnertz, who tragically passed away at the end of last year, and we are all super thankful for his work. And without him, I think we were not here discussing about which complex organic molecule is in the ice. And Harold is, I feel like he's watching us with big smile, because he could be so proud of seeing all these amazing results. And of course, we are also very happy as astrochemists because the future is super bright, and we are waiting for Gravity Plus coming up and already giving us amazing results on the inner disk. So again, complements to what we have already done so far. And also, of course, the Ariel, Plato mission, and the extremely large telescope that we are going to actually look at amazing spectra from probably terrestrial planets. And of course, I put here also the Atlas and GVLA and SKO that we are also all waiting for. So thank you so much for your attention.
Thank you very much for being perfectly on time. So we have 5 minutes for questions. Raise your hands. There.
Ciao Paola, very nice talk, thank you. I was wondering what can JWST tell us about the composition of the dust and not of the ice that is covering the dust?
Right. Yes. So I mostly focused, of course, on the ice because this is what, say, astrochemistry in a sense is telling us. But I am sure that it can tell us a lot also about the mineralogy, because you have now the possibility to see these fissures, like, I don't know, the silicate fissure with very much detail, which of course is also very important to compare to models, say, I don't know, amorphous crystalline, the amount of crystalline silicates in the solids. And I think it's probably even more, so from my point of view, it could be great if we could put some limits, or at least say something about what the ice is actually doing to the solids, because there must be some interaction between, say, ice and solid, and this is what will affect then the mineralogy in the later stages of, say, pebble, planetesimal, and planet formation, because you will mix them all up. So I think there is still need a lot, there is still they need to do a lot of laboratory work and then precision measurements of these features with JWST. So sorry, it's a bit blah, 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 because I don't have yet, say, the results, but I'm sure it will be fantastic. Yeah.
Any other question?
There is one there on the left.
Another one there. Oh, maybe it's the same. Thank you.
Okay.
Thank you very much for this enthusiastic talk and a very interesting talk. So you mentioned that there are a lot of things to be done from the point of view of theory. And I was wondering what you think should be done urgently, what tracks
Yes.
that has to be done.
Yeah, in fact, I mean, we are actually working on this right now very hard. I think we need, first of all, to put together communities, because there are lots of these chemical thoughts available around the world. And in fact, there is an effort that's led by Jimenez Serra, Itascun Jimenez Serra, bringing together many groups around the world, in fact, to look into specifically we will do one molecule at a time to look at the formation, say, of methanol. That is very important. It's a very delicate thing on the surface. We see it, and we cannot reproduce completely, say, what we are seeing. So we are trying to understand. So it's mostly surface chemistry. That is, of course, is our kind of pain point, Achille, tallone d'Achille in the astrochemistry community, because it's very difficult to understand the processes that happen in these tiny grains. We have lots of kinetics done in the laboratory, which is also super important, but there are still things like, for example, interaction with ions in the ice, the cosmic rays that can also penetrate and can do damage, say, dissociating molecules, produce secondary electrons, which can also propagate fast and produce other excited molecules. So all these things need to be taken, you know, with calm, one step at a time, because there are a lot of parameters, but we have to do it seriously now, because with this data, we cannot just mess it up.
Thank you very much. I think. Let's check.
I can say later. Okay, this was actually my follow-up question. For instance, can you estimate the role of X-ray background on the formation of those dust and survival?
Okay, so the X-rays background, so you mean, for example, nearby a young star where we know that there is production. Yes, so there are studies, in fact, also done in laboratory that say look into the X-ray. I think also Sergio Iopolo has done in the past, but other people as well, to look at the interaction of X-rays with icy mantles. And there is, I think it's a little bit difficult. Hopefully with JWST we can do this better now, but it's a little bit difficult to pinpoint the ices that are actually impinged by these X-rays, because this must be a relatively small region around like a class 0 source of these young protostars, because the material is so thick, so you have a lot of column that is absorbing the X-rays. Energetic, so cosmic rays and also energetic particles that are accelerated by this young protostar, they can actually go even deeper because they are more energetic and they go through losses, but they can go deeper into the disk. So this is something that it is being studied. Yeah.
Thank you. The talk was great.
Oh, thank you. Thank you. Very happy to hear.
Let's all thank our speaker again, and let's move to. And let's move to the last talk of this session before lunch. Our last speaker is Giorgio Matt from University of Roma Tre in Rome, of course, in Italy. And the title is X-ray Polarized Sky Results from the Imaging X-ray Polarimetry Explorer.
Okay, thank you very much. It's a pleasure to be here to report on the first results from the first 2 years of the operation of the Imaging X-ray Polarimetry Explorer, XP for short. My main goal here is to show you that even in the era of the multi-billion-dollar facilities, it's still possible to have a lot of fun with a relatively small and cheap mission. Okay. This is the plan of my talk. After a brief introduction to X-ray polarimetry and a little bit of historical remarks, I will describe the mission, the Imaging X-ray Polarimetry Explorer, and then I will report on the results of the first 2 years of operation, the so-called baseline mission. I will explain you later on why it is named. Just a warning, I mean, we have a lot of results and we produced about 10 papers on science, nature, and natural astronomy, which is impossible to report on all these results in half an hour talk. So my review will be inevitably incomplete. I will apologize for those who will not be quoted here. And of course, will also be somewhat biased. Anyway, there will be other talks on XP results elsewhere in this conference, here and there, and in particular in 2 special sessions. The one which is running today, which is SS16, relatively on jets from AGN and the ING polarimetry, and the other one, which is scheduled for Thursday, which is on extended sources in the XP era. So let me start with a brief introduction to X-ray polarimetry. Even if we are now in the starting at least the era of multi-messenger astronomy, still 99.99999% of our information is coming from electromagnetic radiation still. And of course, we want to exploit all what the electromagnetic radiation can, all information that can give us, which means exploiting the spatial spectral timing and polarization properties. In particular, polarization properties can give us crucial information on geometry. Geometry, of course, of the emitting matter in the very often case in X-rays in which your source is not spatially resolved, but also geometry of the magnetic field, the gravitational field, and even the space-time. Of course, the polarization degree depends and therefore gives us information on the level and type of symmetry of the system, while the polarization angle indicates the orientation of the system. So our knowledge of the emission from a celestial source in any energy band is therefore incomplete without polarimetry. And this was in the past particularly sad in X-rays because we expected polarimetry to be particularly important in X-rays where non-thermal and aspherical situations are very, very common. So it was very sad that polarimetric information was basically missing before XP. Just in a nutshell, what polarization can tell us? Well, we have several processes which can result in a significant polarization. Scattering, of course, is the most obvious one. In this case, we expect a polarization angle perpendicular to the scattering plane. Synchrotron radiation is the obvious emission mechanism producing high level of polarization. In this case, the polarization angle is perpendicular to magnetic field lines. General relativity can also affect the polarization properties, causing rotation of the polarization angle and, in this sense, a sort of depolarization of the emission. And in very highly magnetized plasma, we can have very strong polarization signal because of the different opacity of the plasma to the 2 different polarization modes. And before XP, only one positive measurement, the measurement of the Crab Nebula averaged over the entire nebula, 90%, was obtained, dating back in the 70s, so very, very long ago. This 90% obviously demonstrated that the nebula was emitting synchrotron radiation. But after that, no X-ray polarimeters were put on board of X-ray satellites, basically because of the mismatch between the proposed polarimeters and the other detectors. The problem was indeed that the polarimeters were not sensitive enough. Now, fortunately, sensitive enough polarimeters do exist based on photoelectric effect, a little bit of word later on how this works. And so, in the end, the Imaging X-ray Polarimetry Explorer was selected by NASA in 2017 in the framework of this MEX program and launched in December 2021. Okay, so now a brief description of the mission. here is the main information, is a joint venture between NASA and Italian Space Agency, within, as I say, the NASA Small Explorer program. It was launched successfully on December 9, 2021, put on a 600-kilometer circular orbit at the nominal 0 degrees inclination, which ensure a low and stable background. At the beginning, the mission was funded for 2 years, the so-called baseline mission, in which the observing program was devised by the XP team, and now has been extended with the general observer program. Classical point-and-stare technique at pre-selected targets. And another important information is that there are no proprietary rights because of NASA rules, and neither in the baseline nor in the present geophase. So data become immediately public after the observation. Okay, this is the institutions involved. As I say, it is mainly NASA and Italian Space Agency mission, but there is also a small participation by Japan, by the Nagoya University. And the PI is, the current PI is Phil Carret at the Marshall Space Flight Center. Formerly, the PI was Martin Vaskov, and indeed Martin, along with Paolo Soffitta, who is the Italian co-PI, and the XP team, were awarded the Rossi Prize last year. But the XP science team is actually comprised by more than 100 scientists from many, many countries, especially in Europe. In a nutshell, the mission is composed by 3 identical pairs of mirrors focusing X-ray mirrors and detector units with about 5 meter total focal 4 meters, sorry, focal length. Is working the energy range between 2 and 8 kV with a spatial resolution of 30 arc-second, which is good enough for our goals. The field of view is 13 arc-minutes. The energy resolution is not terribly good because it's basically a proportional counter, but still, I mean, is usually, at least for most of our science goal, is good enough. The detection principle is based on the photoelectric effect, on the fact that the direction of the photoelectron is preferentially the direction of the electric vector of the absorbed photon. So what it happens is that it is produced, this track you can see there, and from the direction of the track you can derive the direction of the polarization vector of the absorbed photon. When you collect many photons from a source and plot them the direction on a phase diagram, you will end up with a modulation of the signal, and from the amplitude of the modulation you can derive the polarization degree. Of course, if the source is completely unpolarized, you will have a sum of completely random tracks, and your modulation will be distribution will be completely flat. From the position of the peak in the modulation, you can derive the polarization angle. About the observing program, the XP baseline mission was funded for 2 years, finished on January this year. As I said, the observing program was defined by the XP team. Then a bridge extension till September 2025 was granted by NASA, waiting for the standard call for mission extension, which will occur next year. So after the bridge extension was granted, a general observing program was issued last year. GEO1 started on February this year with a pretty large oversubscription factor of the order of 6. And now the call for the GEO2 proposals is open with a deadline on late August this year. And we will have also joint program with other NASA facilities like NICER, NuSTAR, and SWIFT. It's very important for at least selected science topics to have simultaneous observation by spectroscopic facilities, let's say. Even if we have some spectroscopic capabilities, we are limited by the relatively narrow energy band, even more than by the spectral resolution. So for some cases, at least, especially for variable sources, it's very important to have simultaneous observation with other facilities. And NASA, we have these joint programs to this goal. So now let me discuss the results from the first 2 years of operation. as I say, just a few selected results. Here is the number of sources we observed so far, about 60 sources, covering very different classes of sources. Basically, we observed all classes of X-ray sources, apart from stars, simply because they are too faint, and classes of galaxies, because we expect them to be completely unpolarized. Their X-ray emission is just thermal emission, thermal optically thin emission, so we expect there is no polarization there. Some sources have been revised because we want to observe very often sources in the same source in different states. I will show you some example later on. And but even after 2 years, we have now several tens of sources for which we have good measurement of polarization against the only one source we have before expert. And another important thing to remark is that we have positive detection in the majority of sources. In X-rays, polarization, significant level of polarization is relatively common. In some classes, it's very common. Okay, let me start with pulsar with nebulae. One of the first things we want to check is whether we could recover the OSO7 results, the very old results on the Crab Nebula. We could. When averaging the emission of the entire nebula, we obtain the same result as in OSO8. But of course, we are now an imaging mission, so we can do spatially resolved polarization, which is very important in kind of sources, because here you can see on the left, the Chandra image of the Crab Nebula. You see that it's not spherical at all. It's very complicated. So you expect different polarization in different zones. And indeed, we find very different polarization in very different zones, as expected. And because the average must be 19%, it means that in different zones, you should have much larger polarization than that, in order that when you sum up, you end up with the average 19%. And indeed, we find very high polarization in this kind of sources. In some cases, in some selected regions, very close to the synchrotron limit. Even more striking than Crab is the Vela pulsar with nebula, in which we have an average polarization of 45%, which is really huge, which is in some selected regions is even larger than 60%, so very, very close to the synchrotron limit, which means that in this selected region, the magnetic field is extremely ordered. You don't have any turbulence, you don't have any, it's really like that. So these results suggest indeed that the magnetic field is less turbulent than expected by many models. In general, polarization is consistent with radio, at least in terms of alignment, but X-rays sample regions much closer to the site of acceleration, because it sample much more energetic electrons before they lose energy by synchrotron emission. Another interesting source is the so-called cosmic end. It's a more complex pattern here, but at the base of at the end of the jet, we found a polarization which is even in excess of 70%. So it's really, really at the synchrotron limit. Regarding supernova remnants, classical supernova remnants, here, of course, the overall polarization is much less. Not surprisingly, because the emission here is mostly thermal. But when you select only the high energy tail, the synchrotron tail of the emission, we can find relatively high polarization, which goes from 4% for Caselli, 12% for Tycho, and 22% for SN 1006. So increasing between the sources, which clearly suggests a different level of turbulence, and we don't know exactly why. Maybe it's related to the ambient medium. And in all these cases, the magnetic field is radial, near the particle acceleration site. So at the very least, we have found some common behavior, unless we found a new source in which, however, in a particularly selected region, the magnetic field is tangential. So again, we have a lot of results to think over before understanding fully what is going on. Anyway, if we are interested in this kind of science, this will be discussed in detail in the special session on Thursday. Still on extended sources, a very nice result is regards Sagittarius A star, our own black hole, the black hole in our own galaxy. You know that in the central region of our galaxies, there are a number of molecular clouds, which are bright in X-rays. And clearly from the spectrum, these sources are just reflecting radiation from external sources. The problem is that at the moment, there are not bright enough sources in the galactic center to explain the luminosity of these molecular clouds. So it has been suggested in the past that they are just reflecting X-rays from Sagittarius star, which in the past has a sort of echo. So in the past, it means the Sagittarius star should have been much more brighter, of the order of 10 to the 6 times brighter, so at the level of a low luminosity AGN. There are several arguments in favor of this scenario, but with polarimetry, you can prove it, you can provide a sort of smoking gun, in the sense that if these are really reflecting radiation from the Sagittarius star, you expect this radiation to be highly polarized, and with the polarization angle, because the polarization angle is perpendicular to the plane of scattering, which is perpendicular to the direction of the incoming photons. So from the polarization angle, just taking 90 degrees, you can see where the photons is coming from. So we observe one of these clouds. Unfortunately, these clouds are dimming nowadays, so there was one bright enough, and with relatively long observation, more than 1 megaseconds, we can find a relatively good measurements. It's still a little bit short of a classical 3 sigma results. It's only 2.7 sigma, but the polarization angle is exactly what you expect. You see here in this polar plot that the polarization here is the preferred polarization angle, which is exactly perpendicular to the direction from Sagittarius star. So even if it is a marginal detection, let's say so, is confirming the overall scenario. It's confirming that the radiation is really coming from the Sagittarius star. From the polarization degree, you can in a sense map the 3D position of these clouds, because of course if the scatterings at 90 degrees, you have the maximum of polarization, and then reducing if the source is scattering at less than 90 degrees. Of course, it's degenerating in the sense that we have two solutions, and the two solutions give us, and when you translate the distance of, when you put the source in 3D space and then translate it into in EAS from the burst that provoke this reflected radiation, we can find two possible solutions: 30 years if the source is here, 200 years if the source is there. And 30 years doesn't look reasonable, because 30 years ago we have already a lot of X-ray satellite, and if the galactic center was 1 million times brighter than now, it would have been the brightest X-ray source in the sky after the sun, so we should have seen it. So it's very likely that this molecular cloud is on the far side, and so the burst occurred 200 years ago. Probably our non-galactic center just, there was a sort of just a star passing by and eaten by our own black hole. Magnetic fields are, of course, very strong magnetic fields are, of course, obvious targets for an X-ray polarimeter. We observe magnetars, which are the most extreme among magnetized sources. They are neutron stars with magnetic field up to 10 to the 15 Gauss, really amazing values. And in this scenario, you expect a lot of polarization, because there are two modes: the ordinary modes in which the electric field of the photon is parallel to the magnetic field, and the extraordinary mode in which it is perpendicular. And what is important is that in a highly magnetized plasma, these two modes have different opacities. So you expect that X mode would come from deeper outer layers. So you expect in the end strong polarization. We observed two sources basically. The first one shows a polarization angle swing of 90 degrees. At low energy is in a certain direction. At high energies is the 90 degrees away direction, which means that there are two different modes, which are probably due to thermal emission and to Compton scattering emission. And the overall relatively low polarization, relatively in the sense that we have also 30 or 40% polarization degree, but for this kind of sources is relatively low, seems to indicate that there is no atmosphere if you look at the models, which are very complicated, we can, from this relatively low polarization, we can already favor one of the models respect to others. In another source, instead, we have still two components, but with the same angle. So it looks like the same mode is dominating. But in this case, the polarization degree is very high, and at very high energy, still within the errors is even consistent with a completely polarized emission. I skip this one because I don't have much time. So, I want to discuss a little bit about so-called microquasars, so accreting stellar mass black holes in our own galaxy. In this source, in this X-ray binaries, you have a normal star, let's say, transferring mass to a black hole. Then an accretion disk forms. In some particular states, also a jet is formed. And there are it's a very complicated phenomenology. There are several states, but just to simplify things, there are two main states. One is the so-called hard state, in which probably the accretion disk is truncated at a large radii, and then there is a not flow, which is producing the bulk of X-ray emission by Comptonization. And then there is a soft state in which instead the accretion disk is extending down to the innermost stable circular orbit. And in this case, the X-ray emission is dominated by thermal emission, this black body emission from this accretion disk. And in the hard state, you usually observe also radio jets. In soft state, you do not observe these jets. We observe, first of all, the most famous among the sources of this class, Cygnus X1, very well-studied source. Of course, I mean, if you have a coronal emission or even a thermal emission, of course, you expect much larger polarization if your source is observed at very high inclination, so close to edge on, rather than phase on, because phase on you are more symmetric and your polarization is very low. In this source, we know the orbital inclination of the system, which is 30 degrees. So we expect the polarization of the order of 1%, but instead we found a polarization degree of 4%, much, much higher. So this points to a misalignment between the inner accretion flow and the orbital plane, or alternatively to a relativistic flow of the corona, because in this case, because of special relativity effect, you are effectively observing an intrinsic emission which is at higher inclination than really the inclination of the system. Another important result is that the polarization angle is parallel to the radio jet, which favors a flattening, comparing to the models, favors a flattening configuration of the emitting region. This corona is something above the accretion disk. Then we observe the source in the soft state. We found the polarization half the value, but the polarization angle is still parallel to the radio jet, which was surprising because from thermal emission, we expected the polarization which should be parallel to the disk. The only solution we have for that is to invoke returning radiation. I mean, if you have radiation from the disk emitted very close to the black hole, then because of gravitational lensing, you will have that this radiation partly goes back to the disk, and this produces a polarization which is perpendicular to the disk. But to have that, you have to have a very large spin, because otherwise the disk doesn't extend close enough to the black hole. So if this solution is the correct one, it implies that the spin is very large. I skip this one, and this is my last source, I'm afraid, because time is running out. And another microquasar, which is a transient, this one, Cygnus S1 is a persistent source. This was a very, very bright transient, which started its outburst in August 2023. And it was first in hard state. We observed it during September, October. Then the source became not longer visible by X-ray due to some constraints. And then we observed it again when it became visible again in February, April. And first it was in soft state and then back to hard state. In the first observation, we found results very similar to Cygnus X1, polarization of the order of 4%, probably aligned with the radio jet. We don't know because we don't have a resolved jet, but we have a submillimeter polarimetry, which indicates, and usually the polarization vector in the submillimeter is aligned with the jet. So because our X-ray polarization is aligned with the submillimeter polarization, we assume that it's also aligned with the jet. So very similar to Cygnus S1. Then we observed it after several months in soft state, and the polarization was very low, it's only an upper limit. And then it went back on the hard state, but 2 orders of magnitude fainter. And the polarization was exactly the same as 6 months before. So even if the source was 2 orders of magnitude fainter, so probably the accretion rate was 2 orders of magnitude less, the polarization degree and angle was exactly the same, which suggests that despite the large difference in accretion rate, the basic geometry was still the same. Because time is running out and my chairman is getting angry and hungry, probably, I will just go to I will skip, unfortunately, AGN of any sort because of lack of time. Okay, I just leave you this overall summary of the X-ray results. Thank you very much.
Thank you very much. Despite being so close to lunch, you have time for question. Wave your hand or sandwiches, one over there.
Thanks a lot for a very nice overview. I have a question about the galactic center clouds. If they were energized by an outburst, a transient outburst only 200 years ago, would you expect them to show variability on observable timescales?
Yeah. I mean, of course, we don't know how long was this outburst. We know simply that these molecular clouds are varying in time. For instance, when they were discovered 30 years ago, there was one which was much brighter than the one we observed, the Sagittarius B2, which went down very quite quickly. So now it's almost invisible. The idea is that actually this probably was the brightest outburst of, but probably there were more of them because if you look at the various molecular clouds and the times you expect to have passed, I mean, probably just one outburst is not enough.
Thanks a lot.
You need a more complicated pattern.
If you want, we have time for one more question. One up there on the stairs.
Could you please tell something about the confirmation of the obscuring torus in comptotica gens?
Oh, yeah. I haven't shown it because it was probably the only results which were completely expected. So yes, we observed, of course, the obscured AGN, comptotic AGN. There is a torus or something like that, some axisymmetric cold matter configuration. So we expected a very large polarization degree from this kind of sources, and indeed we found very large polarization degree. So it was a brilliant confirmation of the theory.
Thank you very much again, and let's thank all our speakers for this morning.